Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1292, maximum side length of a square with sum less than or equal to threshold. This problem challenges us to apply our knowledge of prefix sums and optimize for the largest square meeting specific constraints. Let's dive in and break it down step by step. We are tasked with finding the maximum side length of a square submatrix within a given matrix math such that the sum of its elements is less than or equal to a specified threshold. If no such square can be found, we return 0. The input matrix mat is a two-dimensional list of integers, with dimensions ranging from 1 by 1 to 300 by 300. The threshold is an integer between 0 and 100,000. The output is a single integer representing the largest possible side length of a square submatrix that satisfies the condition. For example, if the matrix has dimensions 3 by 7 and the threshold is 4, we need to locate the largest square submatrix where all elements together sum to 4 or less. For the first example, the input matrix is provided as a 3 by 7 grid, and the threshold is 4. The output for this example is 2. This means the largest square submatrix that has a sum less than or equal to 4 has a side length of 2. The specific submatrix is shown here, composed entirely of ones. This submatrix confirms the condition since the sum of all its elements is 4, meeting the threshold exactly. No larger square can be formed under this constraint. In the second example, the input matrix is a 4 by 4 grid where every element is 2, and the threshold is 1. Here, the output is 0. This indicates that no square submatrix, regardless of its size, has a sum less than or equal to the threshold. Since every element in the matrix is greater than 1, even the smallest possible square, a 1 by 1 submatrix, exceeds the given threshold. Therefore, the result is 0, as no valid submatrices exist for this case. The third example uses a 3 by 3 matrix with varied values and a threshold of 15. The output for this example is 2, showing that the largest square submatrix with a sum less than or equal to 15 has a side length of 2. This submatrix includes the top left corner of the matrix, with elements 1, 2, 4, and 5. The sum of these values is 12, which satisfies the given threshold. While a larger square could theoretically include more elements, their combined sum would exceed the threshold, making them invalid. To ensure the solution handles all scenarios, we need to consider several important edge cases. For a 1 by 1 matrix, the problem simplifies to checking if the single element is within the threshold. When the threshold is very large, the largest possible square submatrix should be returned. For a 300 by 300 matrix, the solution must operate efficiently without exceeding time or memory limits. Additionally, matrices where all submatrices exceed the threshold must return 0, as no valid submatrix exists. In uniform matrices, where all elements are the same, the solution still needs to determine the largest valid square based on the threshold. Key observations for solving this problem include using prefix sums to calculate submatrix sums in constant time after pre-processing, and applying binary search to optimize the search for the largest valid side length. To solve the problem of finding the maximum side length of a square with a sum less than or equal to a given threshold, we first considered a brute force approach. The idea here is to iterate through all possible square submatrices in the given matrix. Starting from each top left corner, we calculate the sum for every square submatrix of increasing side lengths, from 1 up to the minimum dimension of the matrix. However, this approach is computationally expensive. Calculating the sum for each square involves iterating over all its elements, which takes k squared, time for a square of side length k. Since we would repeat this process for every top left corner in the matrix, the overall complexity grows to m n min 2. This makes the brute force approach impractical for large matrices due to the repeated calculations of overlapping areas. For this reason, we ruled out the brute force approach early on. Instead, we considered an optimized approach using a prefix sum matrix. This method pre-processes the cumulative sums of all rectangular submatrices in a way that allows us to calculate the sum of any square submatrix in constant time. First, we build the prefix sum matrix, where each entry represents the sum of the submatrix from the top left corner to the current position. Then, for each possible side length k, we iterate over all valid top left corners where a square of size k fits within the matrix. Using the prefix sum matrix, we can compute the sum of any square submatrix in O(1) time. To further optimize, we employ binary search over the side length k to find the largest possible square that satisfies the sum condition. This approach has a pre-processing complexity of O(m*n) for the prefix sum matrix, and finding the maximum side length involves O(m*n*log min him n. Its efficiency and simplicity make this method a strong candidate for solving the problem. Another approach we explored was the sliding window technique, which dynamically maintains the sum of the current square submatrix as the window moves across the matrix. This avoids the need for pre-processing but requires careful bookkeeping to update the running sum as the window slides. While this method has a similar time complexity of O(m*n*log min him n, it is more challenging to implement correctly and debug. The dynamic updates add complexity, particularly in ensuring that the window boundaries are managed consistently. As a result, while the sliding window approach is theoretically efficient, it is less straightforward than the prefix sum method. For this reason, we opted not to use it in our final solution. Ultimately, we chose the optimized approach using the prefix sum matrix. While the brute force method is simple, its inefficiency makes it unsuitable for large inputs. The sliding window method is more efficient but harder to implement and debug. The prefix sum approach strikes the right balance between efficiency and clarity. By leveraging the prefix sum matrix, we can compute the sum of any square submatrix in constant time, and binary search over the side length ensures that we maximize the square size efficiently. This combination of speed, simplicity, and scalability makes the prefix sum approach the optimal choice for solving this problem. To solve this problem, we aim to find the largest square submatrix in a given matrix, such that the sum of all elements within the square does not exceed a specified threshold. First, we need to understand the constraints. We are working with a 2D matrix of size m by n, and our goal is to determine the maximum side length of a square that meets the sum condition. To achieve this efficiently, we use a 2D prefix sum array. The prefix sum array helps us compute the sum of any submatrix in constant time. The formula for calculating the prefix sum at a cell involves adding the current matrix value to the sums above and to the left, while subtracting the overlapping region. Special care is taken for boundary cases, such as when the current cell is in the first row or column, or some terms may not apply. This pre-processing step sets the foundation for efficient calculations as we search for the largest valid square. Now, to find the largest square, we start by examining the smallest possible size, which is 1 times 1, and gradually check larger sizes. For a square with a given top left corner at coordinates I, j, and side length k, the sum of the square can be quickly computed using the prefix sum array. This formula subtracts areas outside the square while adding back the overlapping region that was subtracted twice. If the sum of this square is within the threshold, we update the maximum side length found so far. To further optimize, we can use binary search instead of iterating through all possible side lengths. By applying binary search to the side length, we efficiently determine the largest valid square for each starting position. Additionally, handling edge cases is crucial. For example, if the matrix is empty, or even the smallest square exceeds the threshold, we return 0 immediately. Careful handling of boundary conditions prevents out-of-bounds errors during prefix sum calculations. There are several key insights that make this algorithm efficient. First, the use of a prefix sum array allows us to compute the sum of any submatrix in constant time, which significantly reduces the computational cost compared to summing elements directly. Second, binary search on the side length narrows down the search space, avoiding redundant calculations and making the approach scalable to larger matrices. Lastly, proper handling of edge cases, such as empty matrices or boundary conditions, ensures the algorithm is robust and can handle all inputs gracefully. The main data structures involved include the input matrix, which contains the integer values, and the prefix sum array, which is a 2D array of the same size. The prefix sum array allows us to access the cumulative sum of any submatrix in constant time, making it a critical component of the solution. The algorithm relies on 2 key operations. First, we compute the prefix sum array by iterating through each cell of the matrix. This preprocessing step has a time complexity of O(m*n), where m and n are the dimensions of the matrix. Second, for each top left corner of a potential square, we use binary search to determine the largest side length that satisfies the condition. The binary search operation has a complexity of O, log, min, m, n, and since it is performed for each cell, the overall complexity of the algorithm becomes O, m*n*, log, min, m, n. Several optimizations make this approach highly efficient. By leveraging the prefix sum array, we avoid redundant computations when calculating submatrix sums. Binary search further reduces the number of side lengths we need to check, and early termination ensures that we stop checking larger sizes as soon as a smaller size fails the threshold condition. Together, these optimizations ensure the algorithm is both fast and scalable. Here, we start by defining the max side length function within the solution class. The goal of this function is to determine the maximum side length of a square in the matrix mat such that the sum of its elements does not exceed the given threshold. First, we calculate the dimensions of the matrix M and N, which represent the number of rows and columns, respectively. Next, we compute the prefix sum for the matrix to enable efficient calculation of submatrix sums later. The prefix _sum matrix is initialized with an extra row and column filled with zeros to simplify boundary calculations. Using a nested loop, we populate the prefix _sum matrix. For each cell, we add the current matrix value, the prefix sums from the top and left, and subtract the overlap from the top left diagonal. This formula ensures that the prefix sum for any given cell represents the sum of all elements in the submatrix from the top left corner to that cell. After constructing the prefix sum, we move on to the main part of the algorithm, which involves a binary search to find the maximum side length. To help with this, we define a helper function _sum that calculates the sum of any square submatrix given its bottom right corner and size, using the prefix sum array. Finally, we initialize the binary search range with left set to 0 and right set to the smaller dimension of the matrix, and we also initialize max_side to store the result. Now, we proceed with the binary search process. For each iteration, we calculate the midpoint mid of the current range, which represents the candidate side length we are testing. We initialize a flag found to check if a valid square of this size exists. Using two nested loops, we iterate over all possible bottom right corners of a square with side length mid. By calling the square_sum function, we calculate the sum of elements for each candidate square. If the sum is less than or equal to the threshold, we set found to true and break out of the loops since we only need one valid square to proceed. If a square of this size is found, we update max_side to mid and adjust the binary search range to explore larger sizes by setting left to mid +1. Otherwise, if no valid square is found, we reduce the search range by setting right to mid 1. The loop continues until the binary search completes, and at the end, we return max_side as the maximum side length of a square that meets the threshold condition. In this implementation, we begin by defining a method max side length that takes a 2D matrix mat and a threshold value as inputs. The goal is to determine the maximum side length of a square whose sum of elements does not exceed the given threshold. First, we calculate the dimensions of the matrix M and N, representing the number of rows and columns respectively. Next, we compute the prefix sum for the matrix. This is done using a 2D array called prefix sum, where each element at position I, j, stores the sum of all elements in the rectangular region from the top left corner, 0, 0, to the position I1, j1, in the original matrix. The prefix sum is calculated iteratively by adding the current matrix element, the prefix sums from the row above and column to the left, and subtracting the overlapping region to avoid double counting. This pre-processing step allows us to efficiently compute the sum of any submatrix in constant time. Now, we use binary search to find the maximum possible side length of the square that satisfies the threshold condition. We initialize the search range with left as 0 and right as the smaller of M and N, since the side length cannot exceed the dimensions of the matrix. The variable max side keeps track of the largest valid side length found so far. For each potential side length mid, we iterate over all possible top left corners of the square, ensuring that the square fits within the matrix boundaries. Using the prefix sum array, we calculate the sum of elements within the square in constant time. If this sum is less than or equal to the threshold, we mark it as valid by setting found to true and break out of the inner loops. If a valid square is found, we update max side and adjust the binary search range to explore larger side lengths. Otherwise, we reduce the search range to consider smaller squares. Finally, the method returns max side as the result. To solve this problem, we start by computing the prefix sum of the matrix. The prefix sum table is initialized as a 4 by 4 matrix filled with zeros. This extra row and column simplify our calculations by handling edge cases for submatrices near the boundaries. The formula for filling the prefix sum at position I, j, is based on adding the value of the current cell in the original matrix to the prefix sums of the top, left, and top left diagonal regions. Specifically, it's calculated as prefix underscore sum I, j equals mat I1, j1 plus prefix underscore sum I1, j plus prefix underscore sum I, j1 prefix underscore sum I1, j1. Starting with an empty table, we fill in row by row. After processing the first row, the table reflects cumulative sums for just that row. As we move to the second row, the values include sums of the first two rows, and so on. By the time all rows are processed, the table allows for quick computation of any submatrix sum using only 4 table lookups. This structure is a critical optimization for efficiently handling the problem constraints. With the prefix sum table ready, we now perform a binary search to find the maximum side length of a square where the sum is less than or equal to the given threshold. We start by setting left to 0, right to the smaller dimension of the matrix, and max underscore side to 0. The binary search works by testing midpoints between left and right. For mid equals 1, we check all 1 by 1 squares. Each of these has a sum derived directly from the original matrix, and since they all satisfy the threshold condition, we update max underscore side to 1 and move left to 2. For mid equals 2, we examine all 2 by 2 squares. The top left 2 by 2 square, for instance, has a sum of 8, which is valid, so we update max underscore side to 2 and adjust left to 3. However, for mid equals 3, the only 3 by 3 square exceeds the threshold with a sum of 36, so we decrease right to 2. The binary search concludes with a maximum side length of 2. In this second example, we repeat the same process with a new input matrix and threshold. First, we compute the prefix sum table. Starting with an empty table, we fill it row by row. After processing the first row, the cumulative sums reflect values for that row alone. Adding the second row updates the table to include sums for the first 2 rows, and similarly for the third. This results in a fully populated prefix sum table, which allows efficient queries for any submatrix sum. Next, we apply binary search. Starting with left at 0 and right at 3, we test midpoints. For mid equals 1, we check all 1 by 1 squares. Since each square satisfies the threshold of 4, we update max underscore side to 1 and adjust left to 2. For mid equals 2, we check all 2 by 2 squares. These exceed the threshold with sums of 8, so we reduce right to 1. The search ends with a maximum side length of 1. In this final example, we again follow the same procedure. First, we compute the prefix sum table. Starting with an empty table, we fill it row by row. After processing the first row, the cumulative sums account for that row. Adding the second row updates the table to include sums for both rows, resulting in the final prefix sum table. With this in place, we move to binary search. Setting left to 0 and right to 2, we test midpoints. For mid equals 1, we check all 1 by 1 squares. Since each square satisfies the threshold of 10, we update max underscore side to 1 and adjust left to 2. For mid equals 2, the only 2 by 2 square exceeds the threshold with a sum of 20, so we decrease right to 1. The binary search concludes with a maximum side length of 1, which is returned as the result. Here, we start by understanding the time complexity of the algorithm, which is broken into 2 main steps. The first step involves computing the prefix sum matrix. This matrix allows us to calculate the sum of any submatrix in constant time. To construct it, we iterate through the entire input matrix mat, which has dimensions m by n. For each cell in the prefix sum matrix, we perform a constant time operation using its neighboring values and the current cell value in mat. Since we process each cell exactly once, the time complexity for this step is O, m asterisk n, where m and n are the number of rows and columns in mat, respectively. This step lays the groundwork for efficient square sum calculations in the next part of the algorithm. Now, the second step of the algorithm involves binary search to determine the maximum side length of a square that meets the threshold condition. The binary search operates over possible side lengths, with the range being from 0 to min, m, n. This means we can have at most O, log, min, m, n iterations. For each side length mid, we need to verify all possible squares of that size within the matrix. The number of valid starting points for these squares is approximately m mid plus 1 asterisk n mid plus 1. In the worst case, this results in evaluating all potential squares for the largest side length, leading to O, m asterisk n checks. Since we use the prefix sum matrix, calculating the sum of any square is done in constant time. Overall, the time complexity of this step becomes O log min m n asterisk m asterisk n. Combining this with the prefix sum computation from the first step, the total time complexity of the algorithm simplifies to O log min m n asterisk m asterisk n, as the binary search step dominates. Shifting to space complexity, the main contributor is the prefix sum matrix. This matrix has dimensions m plus 1 ejx n plus 1 to handle edge cases during some calculations, which requires O m asterisk n space. Beyond this, the algorithm uses a few additional variables such as left, right, mid, max underscore side, and counters for the loops. These variables occupy a constant amount of memory, which is O1. Since the space required for the prefix sum matrix dominates, the overall space complexity of the algorithm is O m asterisk n. This efficient use of space ensures that the algorithm scales well even for larger matrices. When comparing this approach to a brute force method, the efficiency gains become evident. A brute force solution would involve iterating through all possible squares in the matrix and directly summing their elements. For a square with side length side, summing its elements takes O side caret 2 time. Given the total number of possible squares in the matrix, the time complexity of brute force becomes O m asterisk n asterisk side underscore max caret 2, where side underscore max is the maximum possible side length, or min m n. In contrast, the current algorithm avoids this inefficiency by leveraging the prefix sum matrix for constant time sum calculations and binary search to narrow down the number of squares we need to check. This optimization reduces the time complexity to O log min m n asterisk m asterisk n. Mathematically, the binary search drives this efficiency by limiting the iterations to O log min m n while still ensuring accurate results. Finally, let's analyze the algorithm across different scenarios. In the best case, where the threshold is very small, the binary search terminates early because most squares are invalid. Here, the complexity reduces to approximately O m asterisk n, as fewer squares are checked. In the average case, for a moderate threshold, the binary search performs O log min m n iterations and the checks are reasonably distributed across valid squares. This keeps the complexity at O log min m n asterisk m asterisk n. In the worst case, where the threshold is very large and almost all squares are valid, the algorithm performs the maximum number of checks. Even in this scenario, the complexity remains O log min m n asterisk m asterisk n. Thus, the algorithm is robust and maintains efficiency across different input constraints. When solving this problem, there are several common pitfalls to be aware of. First, an incorrect prefix sum calculation is a frequent mistake. Remember that when constructing the 2D prefix sum matrix, you need to properly account for overlaps. The formula includes adding the values from the row above and the column to the left, but subtracts the overlapping area in the top left corner. Forgetting this subtraction can lead to inflated or inaccurate submatrix sums. Next, off by one errors are another challenge. These occur when handling matrix boundaries, especially with zero-based indexing. Make sure your loops are carefully designed to avoid out-of-bounds errors when working with different side lengths. Another major issue is relying on a brute force approach. Calculating the sum of every square submatrix repeatedly leads to a time complexity of O n to the power of 4 in an nxn grid, which is far too slow for larger inputs. Additionally, misunderstanding the problem constraints can lead to flawed solutions, such as assuming all threshold values are feasible without considering edge cases like tiny matrices or thresholds smaller than the smallest matrix value. Finally, skipping the use of binary search for optimization can be a significant inefficiency. Instead of incrementally checking all side lengths, binary search allows you to significantly reduce the number of computations, making your solution much faster. To perform well in interviews, it's essential to master several key concepts and strategies related to this problem. First, ensure you have a solid understanding of prefix sums. They are fundamental for reducing the time complexity when calculating sums of subarrays or submatrices. Being able to clearly explain and derive the 2D prefix sum formula demonstrates strong foundational knowledge. Another important concept is binary search on the answer. This problem exemplifies how binary search can be applied to parameterized optimization problems, and you should be prepared to articulate why it works and how to implement it efficiently. Additionally, edge case handling is a critical skill. Be ready to discuss scenarios like an empty matrix, very small matrices, or threshold smaller than the smallest matrix value. Addressing these nuances shows your attention to detail. Finally, being able to evaluate the trade-offs between different approaches such as brute force, prefix sums, and binary search signals your ability to think critically about time and space complexity, which is a valuable skill in technical interviews. This problem is closely related to several other LeetCode problems, which can help deepen your understanding of the underlying concepts. For example, LeetCode 304, Range Sum Query 2D Immutable, is a foundational problem for mastering 2D prefix sums. LeetCode 363, Max Sum of Rectangle No Larger Than K, involves 2D submatrices with constraints, making it a natural extension of the concepts here. LeetCode 221, Maximal Square, focuses on finding the largest square submatrix that satisfies certain properties, while LeetCode 85, Maximal Rectangle, generalizes this idea to rectangles and relies on dynamic programming techniques. Regarding alternative approaches, brute force is the most straightforward but impractical for large inputs due to its n to the power of 4 time complexity. A more efficient method involves using a 2D prefix sum to calculate submatrix sums in constant time, reducing the complexity to n cubed. However, you can achieve even better performance by combining prefix sums with binary search on the side length, yielding an n squared asterisk log n solution that balances clarity and efficiency. Dynamic programming is another approach to consider for variations of this problem. By iteratively building larger square submatrices based on smaller ones, you can efficiently determine the properties of the matrix as you expand. However, incorporating the threshold constraint into this method can be challenging. While DP is powerful for certain types of problems, it may not always be the best choice for this one, especially when compared to the efficiency of prefix sum and binary search techniques. Balancing the trade-offs between these methods is key to selecting the most appropriate solution for the given constraints. Great job! We've successfully tackled this problem using prefix sums for efficient computation. Remember, understanding and applying the right algorithmic tools is key to solving challenging problems like this. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!